Hey everyone, welcome back. Today we're going deep on something that kind of sounds like it's straight out of science fiction. Error-proof quantum computing. And get this, it's inspired by, well, you're not going to believe this, Schrödinger's cat. You know that thought experiment. The one where the cat's in a box and it's like both alive and dead at the same time? Yeah, that one. Now I know what you're thinking. What does some hypothetical cat have to do with actually building quantum computers, right? Well, the big thing is the qubits. They're incredibly fragile. These qubits, the quantum bits that hold information, they're so sensitive. I mean, even the smallest disturbance can cause errors, and it basically just scrambles all the data to really get how delicate these qubits are. Imagine writing with a pencil, but you're trying to do it during an earthquake. That shaky ground, that's kind of like the constant noise and interference that can just completely throw off these delicate qubits. And that's why error correction is so important. I mean, it's absolutely crucial if we ever want to build quantum computers that are, practical and reliable. So, where does Schrodinger's cat fit into all of this? Well, researchers have figured out this, brilliant way to use the idea of superposition. It's the same idea behind the cat being both alive and dead at the same time, to create this, more robust type of qubit. So instead of a cat, they're using an antimony atom, which, this is cool, it could exist in multiple states at once, kind of like a cat in the box, right? But here's what's really interesting. This antimony atom can actually, survive multiple errors before the whole system collapses. It's like we're giving her quantum information, like multiple lives, you know what I mean? Making it way more resilient. And get this, they've managed to actually embed this antimony atom within a silicon chip. The same kind of chips we use in, everything. Our phones, our laptops. This is huge because it means that maybe, just maybe, this approach to error correction could be scalable, which would bring us closer, a lot closer, to a future where quantum computers are a reality. So, okay, let's break down how this atomic cat thing actually helps with this whole error correction thing. See, normal qubits, they have two states. Think of it like a light switch. It's got like 8 spin directions. So it could exist in 8 different states all at the same time. Okay, imagine like a compass, right? Arrow pointing in 8 different directions. Each direction, that's a different quantum state that this antimony atom can occupy. And this is where superposition comes in. The atom's basically in all 8 states at once until we try to measure it. It's wild. And because it has all these multiple states, it can store information redundantly. It's like having backup copies of your data. So if one part of the system, gets hit with an error, the information's still safe. It's still preserved in all those other states. And it's this redundancy that gives our little atomic cat its resilience. It can take multiple hits, multiple errors before any information is actually lost. And that's a game changer for quantum computing, right? But wait, there's another layer to this that makes it even cooler. Remember how I mentioned this antimony atom is embedded in a silicon chip? Well, that's not just some random choice. Silicon, it's the backbone of all our electronics. It's in everything, smartphones, laptops, you name it. So we already have this huge infrastructure for manufacturing and working with silicon, right? So by embedding this atom in a silicon chip, these researchers are they're using existing technology to make this approach to error correction way more practical and potentially even scalable. It's a huge step towards making quantum computers a reality. And so we've talked about the how, right? How this research is pushing the boundaries of quantum computing. But let's take a second to think about the why. Why is this such a big deal? What could these error-corrected quantum computers actually, do for us? Well, imagine designing completely new drugs and therapies. By being able to simulate these really complex molecules at the atomic level, that's just not something we can do right now, even with the most powerful computers. Or picture this, a world where logistics and supply chains are optimized. Incredibly efficient, thanks to quantum algorithms that can handle these huge networks of data. And hold on, what about AI? Quantum computers could completely revolutionize AI. We could develop algorithms that are exponentially faster and more powerful than anything we've got now. And those are just a few examples. Honestly, probably just scratching the surface here, It's like we found this whole new continent and it's full of uncharted territory, all this potential just waiting to be discovered. But there's a catch. And this is where this idea of decoherence comes in. So qubits, they're ridiculously sensitive to their environment, right? Even the tiniest little interaction with anything around them. And they can lose their quantum properties. It's kind of like if you try to build a sandcastle on a beach, but it's really windy, the slightest breeze can just mess up everything you've built. And that's why error correction is so important. It's not even just about fixing errors. It's about preventing them by protecting these super delicate qubits from everything around them, the noise of the world. this research with the whole Schrödinger's cat atom in a silicon chip. It's a big, big leap forward in that quest for error correction. It kind of suggests that we might, actually be able to create quantum computers that are not just powerful, but stable and reliable too. Enough to unlock all these crazy possibilities we've been talking about. And it just reminds you that, like, sometimes the most groundbreaking innovations, they come from the most unexpected places. I mean, who would have thought that a thought experiment with a cat in a box, right, could lead to actual breakthroughs in quantum computing? And that's what makes this whole field so exciting. We're constantly pushing the limits of what we thought was even possible. And who knows what amazing discovery is just waiting for us.